Hi there, welcome again. Let's do this problem regarding truss. So these are truss members or bars, okay, that are subject to two forces going down 20 kilonewtons each force, and it's supported by this hinge over here and this roller here. Basically, what they are asking us is let's get all of these members if they are in tension or in compression, and after that let's calculate the normal stress. Okay, so the normal stress basically it's the axial load or the force subject, whether it's tension or compression, and divided by the cross section area. And they are telling us that the cross section area right away of each of these members is 25 square millimeters. Okay, basically that's the basic idea in order to get them. So this is a little bit, laborious in order to do that, but let's just do it. Let's just do first a free body diagram. So a free body diagram for the whole thing. And the whole thing, I'm going to put this is a hinge A, and the hinge A will feel this reaction going vertical, this reaction going horizontal, okay? And there is a roller here, so this roller will just produce this horizontal reaction or a normal, okay, a normal component. I don't really care about the details of the truss, okay, so far for this free body diagram, but I know that somewhere here and somewhere there are 20 kilonewtons going down, 20 kilonewtons going down. What I care, yes, I care about this 3 meters long and this also 3 meters long, okay, that's important. What I mean by I don't care is that I don't need to know the details of the truss. I'm just taking a global free body diagram. I see the whole truss member is just one big piece of solid. Okay, I don't really care about the individual truss members. Okay, so let's just do this and let's just do the X part. So the X part is RAX going to my right plus RBX going to my right equals to 0, because nobody's there in order to do something else. Let's just go with y. I don't know, but you can add this in the negative part. Okay, so that's the negative minus 20 kilonewtons, these two guys going down. And there is one guy going up plus RIY equals to 0. Therefore, I can get that the reaction going up at the hinge is equal to 20 kilonewtons. Okay, so that's something that I can know kind of right away. Now let's just go with moments. So the sum of moments applied in a particular point, and this particular point, what I'm going to get is A. Okay, most of the times this is a good point because I have two unknowns here and I want to get rid of that in this equation. Therefore, I'm applying sum of moments at that point, and this will mean that these two RAX and RAY won't produce any moment. RBX will produce a moment, so it's RBX multiplied by the distance. So the distance between here and there is 4 meters, okay? So this one is 4 meters, and I need to know that this is producing. So if I'm gonna try to produce a moment like that, that would be positive. Therefore, this guy is producing a moment that it's positive. If you don't know these conventions, you need to go a little bit back and try to see why is that. But it's just a convention about signs when it comes to moments, okay? Most of the time we deal with forces, and forces are a little bit easier to know if they are positive or negative, whether are going left, right, up, or down. But when it comes to moments, you just need to decide, okay, are they going this way or are they going the other way? That's kind of the basic idea. So if they are doing this, it's going to be a negative, and it's they are doing that counterclockwise, it's positive. But it could be the other way around, and it wouldn't be any problem. Okay, so far I'm taking this moment regarding this is a moment produced by the reaction at B going horizontal. Let's just go with this one. So 20 multiplied by 3 and then multiply, no multiply, but let me just put this a minus sign, also 20 times 6, and this one would be equal to 0. Now from here, what I have, if I'm doing things correctly, RBX, it's gonna be equal, well, I can divide everything by 4. This is a 5, and then this is a 6, but then this guy, it's a 5, and therefore what I have here is 45. Okay, so this one over here is 45 kilonewtons. Okay, therefore that means that my from here that my RAX it's going to the left, and that's why it appears with a minus. Okay, so loads, these are the reactions located at A and B. Now let's just get each one of these members. I'm going to use node method, or the method of points, or the method of nodes. So what I'm trying to analyze is what's happening at each one of these nodes. This one is a node, this one is a node, this one is a node, or a joint, whichever name you like. Whether it's a node or a joint, you can actually do it. And this is the laborious part, but okay, so bear with me. Let's just start with B. And if you start with B, you can see that here I have my RBX. Okay, so my RBX is happening here, and I already have it. So I'm going to put 45 kilonewtons. This is my point B. And I have a bar or a truss member, and I need to know if it's tension from going from B to D. Maybe it's tension, maybe it's compression. And I have another guy, and I'm going to call TBA because it goes from B until it gets to A. So that's why it has this name. Okay, so right away I can say, let's just do the Y part. The Y part will give me right away some answers. So the only guy going up or down is TBA. So TBA equals to 0. Okay, so this is a good information. This means that this fellow over here has no load. It has no tension or compression. It's not resisting any force. Okay, it's not doing anything. And you will say, well, then why we have those? Well, we have those because most of the times it's for just stability part. Okay, maybe this 20 won't be all the time 20, and that's why you need to put some other members that will stabilize the whole structure. Okay, now let's just go with X. And the X part, I have this 45 going to the right, plus TBD going to the right as well. Therefore, TBD minus 25 kilonewtons. And then you need to know that this one is in compression. What that means is that instead of trying this TBD, trying to, I don't know, to pull this joint from here, it's actually doing backwards. So it's pushing. I'm going to put it like this. So it's actually pushing this B joint, this truss member BD. It's actually pushing this joint B. Okay, but one suggestion: I never change the drawings. I just only get these numbers, and just looking at the sign, I will know if that is in tension and compression. But I will never change the drawings, because if I change the drawings, I don't know if that was the case at first or I just modified them, and then it's a problem. Okay, so far we already know these two guys. Okay, so we already know about those two guys. Let's just go with another joint, and let me just go with which one we'll see like a good one. Let's just go with E. Okay, so let's just go with joint. Let me just change color. So joint E, it's around here. This is the E. So you have a 20 kilonewton going down. Then you have TED here. You don't know this truss member. And then you have this TE and goes to C. Okay, so now what I can do is that, well, let's just go with the Y. For the Y part, I have minus 20 going down, and I have plus TEC. Okay, so this one is diagonal. Okay, what I'm going to put here, maybe you won't like it. Maybe you work with sines and cosines, because we are used to that from high school. But for me, it's a little bit easier looking at this way. So it's this one, right? So this one has a height of 4. Yeah, so it looks like a height of 4. And this going to the left with 3. So this is a triangle that I can put this vertical part as 4 and this horizontal part as 3. And this is the hypotenuse. So with this hypotenuse, or knowing all these cathets and hypotenuse, I can know the relationship. So how much have I going up? Okay, so the Y part is this 4 divided by 5. 4 divided by 5, and this would give me a number, right? This is actually the sign of this fella. I don't know. I don't really know this angle, but if I knew it, okay, the sign of this angle over here would be equal to 4 divided by 5. I can put it like this. This is sine of alpha if I knew alpha. Okay, so instead of working with angles, you can do it. I most of the times work with distances. Distances allowed me, this is another triangle. This is the slope that has 4 in the vertical part, 3 in the horizontal part. Therefore, the hypotenuse, it's a 5. Okay, how do you know that? Well, 16 plus 9 will give me 25, and you square root that, you will get a 5. Okay, so that's how I manage these components. This is actually a component. Over here is a component going up, the vertical component. Okay, so this one would be equal to 0. You can call it like this. I'm sorry. Let's see there, and TEC Y. Okay, so this is the vertical component of TEC. So therefore, from here, you can know that TEC is going to be equal to how much this is. Okay, so what I'm going to do here is, yeah, so 25 kilonewtons, because I have everything here. This one is in tension. Okay, so I have another one. Now let me go with X. So the X part, I have a minus TED going to the left. This 20 doesn't participate in this equation, and I need the horizontal part. Okay, so it's going to the left, minus TEC, and then a ratio. And this ratio is going to be the horizontal part, 3, remember the triangle, divided by hypotenuse. This is a cosine of alpha. This is a cosine of alpha. Therefore, this one equals to 0. Since I already know this guy, okay, therefore I can get right away that TED equals to minus 15 kilonewtons. That means that this truss member is in compression. Tension means that you want to pull off the joint, or the member wants to pull off the joint, and the compression means that it wants to push in the joint. Okay, that's actually what it's doing. Let's go another. So we already had these guys. Let me just erase a little bit here just to make it a little bit clearer. So we had these guys and I had these guys. Now let's just go with somebody or some of the members happening in the middle. Let me just go with D. Okay, so for D, take a look at D. Okay, no, this one is not. It's not that that maybe you cannot do it, but it's a little bit complicated because I know all these horizontal guys. I know the 20, but I don't know these two guys. Maybe it's not the best choice. I'm gonna use it later, so I'm gonna leave it like that, and let's just go with C. Let's just go with joint C. So joint C is this one over here. So this guy has this one going down, which is called TCD. I don't know it. I think I can have it, this one. Now, I really know this TEC, right? So I already got it, and this TEC is in tension. So if it's in tension here from E, it needs to be in tension here at C, okay? You cannot change. It cannot be at one joint compression and at the other joint tension, because otherwise it would be moving. This thing will be moving. So you cannot put it. Therefore, if this guy TC was tension, so I'm going to draw it as in tension, and I actually know this one. So it's 25 kilonewtons, these kilonewtons, and this one, if you know TEC, okay? And now I have this other AC that I don't know. So I'm gonna put here my TAC. Okay, so now let's just go with the Y part. So the Y part for this one, the Y part is Y part first. Well, it doesn't really matter if you do X part first or the Y part first. But in this case, I think that if I only have this one over here, maybe it's gonna help me. So minus TCD, I'm gonna do it fast. Okay, so minus TCD, minus 25, okay, but only one part of this 25 is going down, not all 25, it's pulling down. Therefore, what I'm going to do, I need the vertical part, so 4 divided by 5, okay, and this one equals to 0. So I always use vertical parts or horizontal parts instead of sine or cosine, okay, and that's my take on this one. So with this, you will get that TCD, if I'm doing these things correctly, it's minus 20 kilonewtons. So this guy is in compression. Okay, so we have another one. Let's just go to let me just erase this one because it can be confusing. Yeah, I have that part. Okay. Okay, so the only ones that are missing, oh my God, what about this guy? I still don't have it. Okay, that's a good one. Now, I'm sorry, what an idiot. I just got TCD. Okay, so let me just, yeah, I have this fella. I still don't have this one. Okay, so now I'm gonna go here and calculate the X part. So the X part for this one, it's gonna be the minus TAC going to the left. And I have this TCD doesn't participate. I have plus 25, 3 divided by 5 equals to 0. Maybe you know that this guy is gonna be just 5. Therefore, TAC, this guy's gonna pass negative to this place. Negative and negative will just nullifies itself, and therefore you have 15 kilonewton. This one is in tension, so that's what you needed to put there. So that's the TAC as in tension. Got it. Okay, so let's just put this one here. Got it. And the only guy that it's missing is this one over here. So I'm gonna do it from A. Okay, maybe it's not the best way to do it, but let's just go at it with A. So for A, let me just change color. Let's just go with this one. So for A, I have A here, and I think let's just go with the reactions first. So I have RAX is actually pulling 25 here. RAY, it's pulling this one up. It's just this one doing this 40, okay? Now let's just go with the members. So this member, remember, I don't know, maybe you remember this one is actually 0. This one is loading nothing, this one over here. Then you have TAC that we just got it. So it was in tension at the other joint. This one is in tension here. I'm gonna put 15, and therefore the only one that I'm missing is this one over here, TAD. So I'm gonna put here TAD. I think I don't know it yet. Let me just see. Yeah, I don't know it. That's why I'm doing this. Okay, so you can use X or Y. Okay, let me just use X. So for X, I will have minus 20, minus 45 plus 15, okay, plus TAD because it's pulling to the right. So, but just the horizontal part, the horizontal part is this ratio equals to 0. Okay, so from here, what you can do is that, well, okay, so let's just divide everything by 3, and you have minus 15 plus 5 plus TAD divided by 5 equals to 0. Therefore, TAD will be equal to, well, you have minus 10 here. It's going to pass as plus 10, so it's a plus 50 kilonewtons as in tension. Okay, so you have it here. Yeah, got it. So you already have all these members, and you can use D just to prove that if that thing is right or wrong. Maybe it's gonna give you a little bit of the creeps, but you can do it. So for example, let's just choose this color, and you have D here. So you have this 20 here, so it's this one. Now, what about BD? Well, BD is in compression. So if it's in compression, BD, it's in compression here at D. So it's pushing. Therefore, will put a 45. Now, what about DE? So I'm here, DE. So DE, where do I have it? Was my ED or DE is the same thing. Therefore, it's in compression. So I'm going to put this 15 kilonewtons here. Okay, so far, I think so good. Now, what about you? CD. Okay, so CD, we got it there, and it's doing this. It's compressing the joint. Here it says compression, so it's compressing the joint. And finally, this diagonal that was called AD. So I'm going to put here AD, TAD, but we already have it as a number, so it was just 50. This one over here was 50. Oh my God, let's just see. It's in tension. So if it's in tension, oops, Let me just put it like this, and then it's in tension. That's important. Otherwise, it could be with a negative sign, and that could be wrong. So now from here, you can say, well, if this thing is correct or not. Let's just go with x. So for x, I have this plus 45. This one, it's going to the right, minus 15 going to the left, and this 50, but not all the 50. So I'm going to put minus 50 because it's going to the left, multiplied by the horizontal part because I need the x part. So 3 divided by 5, and this guy should be 0. Okay, otherwise something is really wrong. Okay, so with that, I will say that this is a plus 30. These two guys are plus 30. This one will give you minus 30 equals to 0. So got it. This thing is in equilibrium, which it is what we wanted. Now, let's go with y. We're just, the problem already is solved, okay? We're just proving this thing is right or wrong. So let's just go with the y part. So I have a minus 20, this one going down. I have a minus 20, this one going down. And these two guys doesn't participate, but this 50 is pulling up, okay? So plus 50, but not the whole 50, just one part. Which part? Well, the vertical part. And these guys should be equal to 0, okay? So this is minus 40. These two guys are minus 40 plus, I hope that you know that this is a 10. And so I will get a plus 40. So everything is correct. Now, just to finish the problem, we have already, we obtain all axial loads of these truss members. We have all of them. The only thing that we need to do is to place all our loads here. So for example, TBD, TBA also, but this one is going to be really easy. But TBD, TC, all of those guys in this formula in order to get the normal stress, okay? So for the normal stress, you can care about the tension compression part, but it's not that important, okay? Now, whether it's doing this, so for example, okay, so this normal stress, okay, you can forget a little. Maybe that's a bad suggestion. It depends on what your professor is telling you or which book you are reading. But for normal stress calculation, it's not very important the sign. Okay, we already did that part in order to get these loads or the forces here. But to get the normal stresses is not very relevant. We needed those signs in order to solve equilibrium. Okay, but now we just care about the mechanics of materials, and that is just the normal stresses. And the normal stresses are not very, we don't care too much about the signs when we are calculating normal stresses. We could, it's just not that important right now. So normal stresses, so it's going to be a normal stress of BA, and this one is the easy one because it's not, there's no force there. And this sigma AD, I have 2 kilonewtons per square centimeter. How do you know that? Well, because I'm sorry. What did I did here? I did something here. Yeah, guys. So I'm sorry. This is not like this. This is square centimeters. Sorry. Does it matter? Well, yes and no. Well, it will change the units, okay? It's not that will change the whole problem, but yeah, this is incorrect. It's not square millimeters, it's just square centimeters. And with that, I have this one, okay? I have these numbers. So this is a normal stress happening for the truss member AD, and then you will have the AC, and this one is equals to 0.6. What I'm doing is just dividing the force by the cross-section area, okay? So everything that I see here divided by 25, and those are the numbers that I'm getting, kilonewton square centimeters. Well, all of them are, I'm just gonna put it here, kilonewton square centimeters in order to save time. And then EC equals to 0.6. Let me just use a little bit more of this column, and ED equals to 0.6. Meanwhile, CD equals to 0.8. You can just put this one in faster and no problem. And then BD equal to 1.8. Okay, so that is the problem solved. Okay, so that's what they were asking us, and that's what we are giving them. Okay, see you guys. I will see you later.